And so these images are intriguing. The question of whether 3i Atlas, for example, shows non-gravitational acceleration, that's still being calculated, debated. That's another important insight about what happened to it when it came closest to the sun. That data is far more interesting. It shows jets, multiple jets going in different directions, and we're yet to see a big telescope imaging those jets. So far, we saw amateur astronomers' telescopes. Maybe there is something really fundamentally wrong with the way we think about the origin of this thing. They don't even bring this up. I mean, I don't have an issue with them claiming it must be natural, but even if it's natural, it seems to me that the main message is that we are missing something. We don't know how such an object is generated.
Most groundbreaking astronomical images come from massive observatories carved into desert mountaintops, but this one did not. It came from a single amateur astronomer standing alone under the cold, motionless sky of the Atacama Desert. What made the moment so unusual was not the telescope he used, which was modest by professional standards, but the atmospheric conditions surrounding him. On that night, the upper air layers stretched out like still water. Wind shear dropped to almost zero. The usual turbulence that bends and distorts starlight simply vanished. In its place was a rare blanket of clarity that astronomers call sub-arc second seeing, a state where the atmosphere becomes transparent enough for small telescopes to behave as if they were far larger. This window does not open often. The desert is known for its dry air and stable sky, but even here the jet stream usually introduces subtle shimmer. On this night the jet stream weakened unexpectedly. Meteorological data later confirmed that a cold air mass descending from the Andes created a stable pocket of air that aligned perfectly above the observer. When 3i Atlas crossed this still region, its light reached Earth almost untouched by distortion. The astronomer also planned his observation with precision. He timed his exposure for the moment when the object reached its highest point above the horizon, minimizing atmospheric thickness. He used long exposures and adaptive stacking, aligning dozens of frames to remove noise while preserving fine structures. Everything worked together. A rare atmospheric calm, a well-timed transit, clean equipment, high altitude. Even the rotation of 3i Atlas slowed slightly from Earth's perspective, reducing motion blur during the capture. For a few quiet minutes, conditions that rarely overlap aligned perfectly. And because of that alignment, the clearest image of 3i Atlas ever recorded emerged from a single backyard telescope. Before this image, scientists relied on indirect measurements to estimate the shape of the 3i Atlas nucleus. Brightness oscillations hinted at an elongated form, but the data was inconsistent. The new photograph changes this completely. In it, the nucleus appears as a defined core, brighter than expected and surrounded by a gradient of faint light that fades outward in a near-perfect curve. This reveals two things. First, the nucleus is larger than most earlier models suggested. Second, the space around it behaves more like a controlled environment than a chaotic one. The elongated shape becomes more obvious under enhancement. The nucleus stretches slightly along the direction of travel, resembling a fragment that broke off a larger body long ago. Its surface brightness is uneven in a way that suggests both reflective patches and darker regions where dust may have accumulated. These contrasts are important because they help scientists understand how the object heats as it rotates. Lighter surfaces reflect more sunlight while darker surfaces absorb it, creating thermal stress that drives sublimation. The glow around the nucleus is even more intriguing. It forms a sharply defined inner layer, unlike the broad diffuse comas seen in typical comets. This layer may represent newly released particles still tightly bound by low energy, or maybe a signature of gas condensation at extremely low temperatures. Either scenario suggests that the nucleus is not ejecting material randomly, but following a pattern governed by internal structure. Scientists are particularly interested in how sharply the brightness decays with distance. The decline is smooth and symmetric, suggesting stable outflow. This kind of stability hints at a surprisingly intact internal composition, something rare for interstellar objects that often arrive fragmented or partially eroded by cosmic rays. For the first time, the nucleus of 3i Atlas is no longer a distant idea. It is a visible, measurable object with shape, structure, and behavior. Comet halos, or comas, are usually chaotic clouds of dust and gas that blur into the background. Their edges flicker with turbulence. Their density shifts as sublimation increases or decreases, but the halo around 3I Atlas defies this pattern. In the new image, the halo appears layered, almost stratified, with boundaries separating one region from another. This is not typical behavior. Stratification usually requires either periodic outbursts or a highly structured internal system capable of releasing materials in distinct phases. The inner halo appears compact and bright, suggesting a continuous source of gas emerging from near the nucleus. This would require a stable reservoir of volatile compounds beneath the surface, heated just enough to sublimate steadily. The second layer is wider and more diffuse. It contains heavier dust particles that move more slowly, creating a band that looks like a faint ring. The third layer fades outward into space, marking the boundary where solar radiation pushes the smallest particles away. This layering is striking because it resembles atmospheric shells around planets or stars, not comets. One explanation is that the nucleus rotates at a rate that causes material to escape more efficiently during certain phases. Each rotation could produce a wave of particles that settles into its own shell. Another explanation involves thermal cycles. If the surface heats and cools rhythmically, these temperature pulses could release alternating layers of gas and dust. What makes scientists most curious is the symmetry. The halo does not sag to one side or show turbulence caused by uneven heating. Everything appears balanced. This suggests that 3I Atlas may have a more uniform surface composition than expected, or that its internal structure distributes heat unusually well. The halo's precision challenges long-held assumptions about how interstellar objects shed material near the Sun. Traditional comet tails form in a predictable way. Dust is pushed outward by sunlight. Ionized gas forms a second tail that aligns with magnetic fields and solar wind. But the tail in the new image of 3I Atlas shows a configuration so unusual that it has already sparked debate among heliophysicists. The tail appears to split into two main components. The first is a broad dust tail, consistent with expectations, although it is thicker than models predicted. The second is a narrow inward curving jet that bends back toward the Sun. This inward jet is the feature that puzzles researchers. Under high resolution, the inward jet maintains a tight beam, even as it extends kilometers from the nucleus. This implies a particle stream dominated by charged ions that follow complex magnetic paths rather than spreading outward freely. The curvature of the jet suggests that 3I Atlas is entering a pocket of the heliospheric magnetic field, where field lines bend sharply. This phenomenon has been recorded around a few rare comets during solar maximum, but never in such clean detail. The dust tail itself reveals new information. The particles are larger than expected, based on the brightness ratio between reflected light and scattered light. Larger particles resist acceleration by solar radiation, explaining the slow, dense appearance of the tail. This means that 3I Atlas may contain heavier material than originally assumed, possibly including metals or complex carbon compounds. The two-component tail structure matches previous hints from spectral data, but this is the first visual confirmation. It tells scientists that the behavior of 3I Atlas cannot be explained by a simple sublimating body. It is interacting with the solar environment in a far more dynamic way, shaped not just by heat, but by the invisible structure of the solar wind. One of the most surprising details in the new image is the appearance of a pulse jet emerging from the nucleus. Instead of a continuous flow of material, the jet is segmented into distinct intervals, almost like beads on a string. Each segment appears evenly spaced, suggesting that the release of material is governed by a repeating process. The immediate question is what mechanism could produce such uniformity. The most straightforward explanation is rotational modulation. If the nucleus rotates in a way that exposes an active vent to sunlight at regular intervals, the vent could alternate between active and inactive phases. As the heating increases, a burst of gas escapes. As the vent turns away, activity drops, leaving a gap. Over time, these bursts align into a visible sequence frozen in space. By measuring the distance between segments, researchers can estimate the rotation period of the nucleus with greater accuracy than ever before. Another possibility involves internal pressure cycles. If the nucleus contains pockets of volatile material beneath layers of insulating dust, pressure could build and release rhythmically. This would create pulsed jets without requiring extreme rotation, speeds. Some comets have shown weak versions of this behavior, but never with the sharp clarity seen in 3I Atlas. The spacing between pulses in the photograph aligns with early brightness fluctuations recorded weeks earlier. This suggests that the jet operates on a stable schedule. The stability is surprising. Interstellar objects often lose structural coherence after long journeys, making their activity chaotic. But 3I Atlas appears organized, almost regulated, in how it releases material. This pulsed jet is more than a visual curiosity. It is a rare natural clock embedded within the object, offering scientists a new way to understand the underlying physics and internal structure of this interstellar traveller. Although the image is monochromatic in its raw form, subtle colour variations appear when analysed through calibrated filters. These variations reveal hints about the chemical composition of 3I Atlas. The dominant green glow, produced by diatomic carbon, matches the expected emission from comets nearing the Sun. However, there are faint traces of yellow and red light near the edges of the halo. Yellow wavelengths often indicate sodium emission. Sodium atoms are released when dust grains fracture or heat rapidly. Their presence suggests that the dust around 3I Atlas contains mineral salts or silicate mixtures, not commonly found in typical comets. Red wavelengths hint at oxygen radicals or complex organics. These compounds form in environments where icy bodies accumulate a mixture of carbon chains, water ice, and metals before undergoing cosmic radiation processing. If confirmed, this would mean that 3I Atlas formed in a region of its home star system, where temperature variations allowed multiple types of materials to coexist. This is scientifically valuable, because interstellar objects serve as time capsules. They preserve chemical signatures from distant systems, offering insights into how other planetary environments evolve. The dust composition also influences how the object interacts with sunlight. Heavier grains heat unevenly and produce slower outflow. This matches the observed behavior of the dust tail, which thickens instead of dispersing rapidly. The light captured in the image therefore functions as both a visual map and a chemical fingerprint. Spectroscopic follow-up observations are already planned. The goal is to determine whether the faint colours correspond to specific molecules or are caused by scattering effects. Either outcome will help refine models of the object's origins. In the meantime, the image provides a rare look into the chemistry of an interstellar visitor that has travelled for millions of years to reach us.